on the lunar South Pole gravity and the search for water.
Thank you.
Again, 12 minutes talk.
Got it? Yep, thank you. Okay, this is motivated by the thought that Maria Zuber and I were kicking around a year or so ago about whether, in fact, the water you see on the surface originally came from the crust or even deeper, and if so, what does it take to make that happen? And in particular, what does the crust show, and does it show anything in gravity? So let me move on. Oh, wrong one. Center one. Which one do I push? Is it? Oh, that one? Okay, thank you. Okay, thanks. Okay, so this is, we start off with the LEN data. I quickly want to go through the LEN data and the PSR issues because it shows up some geometry and such like. So this is the data set that we're one of the data sets that we're working with, and this is the data set that we got from Igor Mitrofanov just 6 months ago in this particular form. It's the epithermal neutrons, and we're going to take a look at this in terms of where the PSRs are and where the LEN data is. We'll put that to bed. We'll look at them whether the LEN data have any connection, at least visually, with the gravity field. We'll try to put that to bed. And then finally to ask, well, what does it take to create gravity anomalies in the surface that we actually see associated with possibly with water or anything else for that matter? Okay. So the first question is, what's the relationship of PSRs and LEN? We've been through this before, but let's go through it again. Okay, here are the two data sets, and I have to be honest with you, what we did was to modify but we took the original data set and we took out the slope.
Can you please stay by the microphone?
Sorry, thank you. The slope across the surface here, and this is actually shown here by Bill Boynton in one of his charts, and we removed that. We weren't sure that we understood what that was about anyway, but it was going to complicate the comparison with anything else. So this is the data set we're actually using. Okay, so over here you see what I call the classical PSR data sets by O.M. Mazarico, essentially from Lola data with all the shadowing and such like taken into account. It's a 400 meter pixel image, and we're kind of looking at these two together here, and you can see the three main craters in the middle there, and you can see the Cabeus and the Shoemaker craters there. So we put them together very quickly, and what we've done here is instead of just plotting a map of the LEN data, we've taken the strongest suppression areas, as I call them, or neutron suppression areas, and plotted them first. This is out of 115,000 points, we plot 500, and you can see the trend. We've seen these before. This is Shoemaker, this is Cabeus. There's another little one over here, a bit on the edge. And if you actually start to increase the amount of data, these spots get larger. Okay, but the point is, when you put them over here on top of the data for the PSRs, yes, you see Cabeus, yes, you see Shoemaker, you see a little bit in Hayworth, which is coming along. But in general, if you were to pursue this much further, you'll see there are many other places which do not tie up. So, yeah, we've got some good examples where it does tie up, and I know more recent data tends to fill in some of these other craters as well, but there are also a lot of places that don't. So let's just move on and agree that to some degree, some things commission, a lot of it doesn't. So it's not in general true. This is just a fuller data set of 5,000. I'll come back to this in a moment. Anyway, quickly looking at this, and the suppression regions don't exactly tie up very well. There are numerous regions where things don't fit, and the bottom line is a PSR is not necessarily, or in general, a neutron suppression region, and reverse. A neutron suppression area is not in general a PSR. Okay, fair enough. So we'll move on now to what the gravity field does. So are the LEN neutron suppression regions associated with locations of crustal Bouguer gravity anomalies, which is really where we started, and asked whether in fact there was anything in the crust that you can see. And when you lay them together, and what you see here is this is the gravity field from 10 to 45 kilometers in depth.
Microphone, please.
Sorry, I'm sorry. Yeah, keep me straight on this one. I walk around. Okay, and you can see these are the gravity anomalies here, and we're going to inspect these in carefully. Okay, and over here are the land observations. They're just in black. These are the biggest areas. I've forgotten how many there are actually in terms of, but anyway, you can see where and there's no obvious pattern associated with in this sense. So to first order, you can say there's no obvious correlation with LEN and gravity, and that's kind of what you expect. However, the point about this is that we're trying to argue whether in fact, or see whether it's possible to get water from the crust into the surface in a sense, and then it can be collected anywhere. So in essence, the source might be somewhere in the crust. It might be just effusing out of the crust somewhere, but it ends up in the PSRs. Okay, so they don't have to be one and the same, but they maybe should be linked in somewhere or other. Okay, so what does it take to do something like this? Next chart. Okay, so quickly, a very simple model. And this is a dimensionless model in a sense. We have a cube. We have a cube of dimensions d, and we put the body, the cube, at a distance d below the surface. So the point about doing this with d and d and d and everything is that with this sphere in this situation, sorry, this cube, you can actually concentrate all the mass at the center of mass here for the moment, okay? And it's a distance d above here, and effectively it's a little bit like a sphere. It works rather uniformly. And so as you go deeper, the block gets bigger, but the same geometric relationship applies. Okay, you put these together, you make yourself a little layer of, say, 25, 5 by 5. So depending on how close you are, that layer gets bigger or smaller. But anyway, in the middle here is quite adequate to explain the gravity. Okay. So we use this model and quickly do calculations. And we take 3 examples of what the density contrast might be in a layer like that, okay? So we start off with saying if the average density of the crust is 2550 kilograms per cubic meter, which is our assumption here, in the general assumption, best estimate for the average crust. So if we make a hole, that's what it amounts to, a delta rho of 2500, it's a hole, then you're following this blue line down here. Okay, so you've got a depth here from 10, 20, 30, 40, 50 kilometers, and you're following the blue line down here. The point is, if you have a hole at, say, 25 kilometers or something like this, it can create hundreds and hundreds of kilograms, hundreds and hundreds of milligals in the gravity field. In fact, we don't actually see that. I'll come to that in a moment. But the example down here is that if you have a 20-kilometer block here, and you follow it up at 30 kilometers total depth in the middle here, then you read it across here and you see 389 milligals are created if you fill that block with water. Of course, you don't want to fill it all with water, but you don't need to fill it all with water. And the same thing is if you put in a somewhat lighter density than the actual crust of, say, 2,000 kilograms per cubic meter, then this is the kind of curve. And we're going to look at these 3 curves with regard to what we see in the crust. Okay, the next point is, what sort of crust do we have? Okay, we've taken this this bandpass, if I might call it, between L equals 120 and 540, and so the upper crust up here, which we don't see because I don't think the gravity data, what I'm using at the moment, will really look at that very carefully. We then look at the next 10 kilometers, which is in this band here and down here, and so 10, 10, 15 kilometers. And we can look at the gravity field ostensibly in those 3 layers, because what I showed you first of all was the gravity field of the whole crust. We're trying to break it into layers. It's not perfect, but it's the best estimate we can have at the moment of what it's like layer by layer. Okay, so let's look at the first one. So this is actually the top 10 kilometers. Sorry, 10 kilometers below the surface, then it's a 10-kilometer block, okay? And so we're looking at some, if you can see it here, it's got all these little blues, little reds, little blues, etc., or yellows, I should say here. And the RMS across it is only 3.9 milligals, a very small amount. The maximum is about 18, minimum 18, 20, and it's in this region. This is Cabeus, this is Scott Crater. This is the only one you can kind of see when you look at the crust. So in other words, at 10 kilometers depth, you see something, but you don't see much above that at all. And there is a high over here, right in the region of Cabeus. I think it probably is in Cabeus, actually. But the point is that you really don't see anything except this randomness, but it's not random. This is actually real data from the point of view we have an almost perfect gravity field at this depth and almost perfect topography to provide almost perfect bouquet gravity. And so this is real. And so when you try to interpret what those variations are, let's just take the RMS, for example, here. Could you explain all that with water? And if so, how much? Well, the bottom line is, you come down to about the bottom here. If you wanted to explain it, you could put 3% porosity in the crust, just vary across the surface, or you could put 5% water, or you could have 15% of some other density of about 2,000 kilograms. The point is, it's a very small anomaly to a very small amount to actually explain. You don't need much water there at these depths. I consider a few percent not large, but some people may say that's a large amount of water. Okay, let's just go one deeper. The point is now that the lower depth you start to see something else. Here we've just shown the lend data on top of it. Lend data as a little smudgy here, I'm afraid, but it's right in within Cabeus, as we expect. Here's the Shackleton one, sorry. Here's the Shoemaker one coming up. Now, Scott is showing up now as a typical crater with rims and a peak. You didn't see this at lower levels in terms of the peak. You did see something of the rim, but not very much detail. Now you see a range now, the RMS of 5.5 milligals. You're now at a greater depth of 20 to 30 kilometers. And if you wanted to explain all these little lumps and bumps around here, all you need is about 1.5% in porosity, which is a very simple explanation, actually, of what you see, and 2.3% in water, for example. Okay, again, in my opinion, not very much. But what this is showing is between here and the previous one is that you didn't see these features, many of these features in the higher 10 kilometers. It shows that I think that first 10 or 15 kilometers or more is completely pounded over and homogenized as a result of impacts and so on. But it doesn't get down to levels where or to the degree you can't still see some of the bigger features as you go deeper. Okay, let's go one more deeper. And here you see now at 30 to 45 kilometers, we're now really getting deep in the crust as well. And you see Scott crater is very well formed, except the center now, thank you, is hollow. The Cabeus has is showing up as a blue area there, although it's there, it's blue, it's low. And you now see these other craters coming up as well in summer, only showing up in depth. Thank you very sorry. Only showing up in depth. But the point is to explain what you see around here, it's only a few percent, like 1.3% in water would take care of all the blues and the reds, plus or minus or thereabouts. It wouldn't explain these. These need to be, this kind of number needs to be about 6 or 7%, some number of that kind. But it explains most of it. So, okay. When we put it all together, this is the whole batch you see right now. You're looking at the original crust that we looked at earlier, and you can see all these features, but this one shows up for a while, always actually. This one's there in some degree, but these others don't appear until the last greatest depth. So let me just run through quickly what, am I looking at the right kind of go? Okay, this is Shoemaker looks like this when you look at the particular profile around 88 south. You just go around that profile and you see the total is quite a large feature, but you don't see it in what I would call in the upper crust. You might see it in the middle crust. In fact, you probably do, and you see it in the lower crust. But I think there's a kind of disconnect. Let's put it that way. So I think this is essentially all a gravity anomaly, got nothing to do with water, and you don't need to kind of connect it to Lend. So the next chart just looks at the other ones, where here we're looking at the Scott crater, and you can see the rim showing all the way up through the crust from top to bottom. Okay, what is Amundsen, which is that big crater on the right, you see a big effect up, it's a total effect. But you don't see anything to speak of in the upper crust. You don't see anything in the middle crust, but you do see it in the lower crust. So these features are showing up at different levels within the crust, and Cabeus is the only one, as a matter of interest, that shows a fairly large low, as we saw it it's very close to, well, it's in Cabeus somewhere. It shows it here. It's not big, but it's there. It's also at low of the next crust, lower down, and it's also in this one, in the deepest crust. So this one is, in my opinion, the only one, believe it or not, of the Lend kind of observation sites, which kind of suggests it might have a gravity anomaly that goes all the way through the crust. It doesn't mean it's water, but it is interesting that in fact it shows something like that. So bottom line is that the conclusions are that we don't see anything in the PSR relationship to Lend is complicated, except we do know the PSRs collect the data. Okay, it doesn't mean to say they're the sources, and there is no general correlation with gravity, except that the crust is homogenized and all beaten up, and the Bouguer gravity field and the Bouguer gravity field does show something for Cabeus as a possible explanation. And there's one other thought associated with this, which is just shown on this last chart, is we don't understand why the Lend data tends to show like this. This is the low data, no hydrogen. This is the positive stuff, and it looks very much. And this, by the way, is South Pole Aching gravity field. Whether that's something to do with these data, with the occurrence of the Lend data or not, we don't know. But it's intriguing that, in fact, they're separated that way. Thank you.
Thank you very much. We have time for one quick question.
So Dave, a crater is a crater is a crater to
Yeah.
first order, right? So why would you have those anomalies in similarly sized structures like Cabeus and Amundsen? They're both, fairly large craters, and yet you really see a distinct difference in
A
their
good question.
reconstruction.
I mean, that's not obvious, okay, but it's clear that in at least one case, the roots seem to go all the way from the surface to the bottom. Okay. Might have something to do with age, of course, okay? And another case, you don't see it until the bottom. So if you assume that the upper layers have been pounded to homogeny, if you know what I mean, okay, as a result of crater, then you could lose all the earlier ones, or some of them, let's put it that way, and some of the others would remain. And I think that happens with Scott. I can't give you a better explanation than that, but it has to be something of that kind, we think, which is something you see at depth of some craters and some